we took up conceptual discussion of this potential and electric dipole and all the things, right? Now, I would like to take up some problems related to this. Some problems related to this. Of course, okay. So what about the material that I have given you? So the type of material I will be sending. Understood? Okay. So apart from this, these are the extra problems. Okay. Yes. So numerical problems on electrostatic potential. The first problem is the difference of potential between 2 points. The difference of potential between 2 points. Between 2 points in the electric field. In an electric field is 6 volt. Okay. How much work is required? How much work is required to move a charge of 300 microcoulomb from the point of lower potential from the point of lower potential to the point of higher potential. To the point of higher potential. Okay. Come on, please note down. The difference of potential between 2 points in the electric field is 6 volt. Okay, after noting down, just keep doing. In the meantime, second problem. If 300 joule of work is done in carrying a charge of 3 coulomb from a place where the potential is minus 10 to another place. Where the potential is V. Calculates the value of V. Next, third one. The positive point charges. The positive point charges of 16 into 10 power minus 10 coulomb and 12 into 10 power minus 10 coulomb are placed 10 centimeter apart. 10 centimeter apart. Find the work done. In bringing find the work done in bringing the two charges four centimeters close. Okay. First, we will discuss. So these are three problems. First, we will discuss these are three problems. Amelia came? Yes. The first problem is the difference of potential between 2 points in an electric field is 6 volt. How much work is required to move a charge of 300 microcoulomb from the point of lower potential to the point of higher potential? Yes, give me answers. 1.8 into 10 power minus 5. Okay, unit joule. Joule, something else you were telling? Joule per second, something you were telling. Mayo. Joule per coulomb. Joule per coulomb. What is the thing that you are going to calculate in this problem? No. What is the thing that you are going to find out? Work. Work unit joule. That's all. No per coulomb. Joule per coulomb is volt, and if at all it is potential, then potential you can represent in terms of joule per coulomb. Okay. Only work we have to find out. So that has to be in terms of joule. 2 point?
1.8 into 10 power minus 3.
Minus 3, not minus 5. Huh? Minus 3 only. Okay. So 1.8 into 10 power minus 3. Okay. Calculator. Same thing? Yes. Okay. For the remaining people say, I will discuss the difference of potential between 2 points in an electric field is 6 volt. Okay. So there are 2 points over here. So the potential difference between the 2 points is 6 volt. So look at this. This is the point A you take, and this is the point B you take. Okay. So the potential between A and B is equal to 6 volt. How much work is also required to move a charge of 300 microcoulomb from the point of lower potential to point of higher potential? Okay, so potential between A to B, A to B, A to B, AB, I have written like this in the sense, what do you say? So this is, its meaning is BA minus BB. So my meaning is BA is more than BB. That means this is a lower potential. Okay, this is a higher potential. This is a higher potential. And what about the charge that is 300 microcoulomb that we are going to take up? That microcoulomb, the 300 microcoulomb should be moved from B to A. This is the direction in which, okay, the charge has to be moved. Okay, so the given charge in this particular case, that is Q is equal to 300 microcoulomb. So that is 300 into 10 power minus 6 coulomb. So this is 3 into 10 power minus 4 coulomb. And what is the formula? Potential between A to B is equal to amount of work done in moving the charge. That implies work done is equal to Q into, so potential between the 2 points. So work done is equal to 3 into 10 power minus 4. And potential between the two things is how much? What is given? Given potential? 6 volt. Okay, so this is 18 into 10 power minus 4. But representing this type of representation is not possible, because scientific notation we have to mention. What do you mean by scientific notation? After every after the first number, the decimal has to come. So that is possible in what way? So this is into 10 power minus 1. Otherwise, 10 power minus 1 we can take out. Sorry. Okay, so this is 1.8 into 10 power minus 3 Joule. 1.8 into 10 power minus 3 Joule. So that is the work done in moving the charge across the potential difference 6 volt. Across the potential difference 6 volt. Okay. Look at the second problem. If 300 joule of work is done in carrying a charge of 3 coulomb from a place where the potential is minus 10 volt to another place where the potential is V. Calculate, V. Calculate V. 110 volt. Minus 110, negative potential. Okay. So potential could be positive or negative. Anything. Potential could be positive or negative. Anything. Okay. So look at this. In this particular case, let me discuss the solution of this. Okay. So if 300 joule of work is done in carrying a charge of 3 coulomb from a place where the potential is minus 10 volt. Okay. So to another place where potential is V. Calculate V. Same thing. Okay. So 300 joule of work done is equal to 300 joule. In carrying a charge has also been given, which is 3 coulomb. Okay. So potential, and if at all we take 2 points, okay, 2 points, right? Okay. So this is VA. So where the potential is minus 10 volt, okay, to another place where potential is V. So this is minus 10 volt. You see, this is the potential V. You see. Then how do you say about the potential difference? V minus 10 is equal to V minus 10 is equal to, so W by 300 by 3. So V is equal to okay, plus only know 110 plus, okay, so plus 110 volt, plus 110 volt. Look at the third one. Okay. Yes. So the third one we discuss. So what is the answer? Third one? 15.5 minus 10 Joule. Ah. So 15.5 into 10 power minus 7 Joule. So this is what Sachin says. Sagar, what's our answer here? Right. Shall I do third one? Okay, shall we work out? Any more answers? Third problem. The positive point charges of 16 into 10 to the power minus 10 coulomb and 12 into 10 to the power minus 10 coulomb are placed 10 centimeter apart. Find the work done in bringing the two charges 4 centimeter closer. 4 centimeter closer. Okay. Thinking. Many people are thinking. Very good. What, yeah, not feeling well? Please see, Abhishek. Not well? Hello? Answer my question, man. Not simply down the head, also downing the head. Not feeling well? Yes or no? No sleep, I think, last night. Because if at all your health is not good, then you take rest. You go to hospital and sleep. Yes. Mayur, what do you say? 4.82. 4.82. Okay. Girls, calculator, Maheshwari, Amulya, Akhilesh, your answer please. Swati, what do you say? Answer. Okay, so I will explain. So look at this third one. So two positive charges, 16 into 10 power minus 10 coulomb and 12 into another, so 10 power minus 10 coulomb, are placed in a distance of 10 centimeter apart. Find the work done in bringing the two charges 4 centimeters closer. Do one thing, Abhishek. Okay, you go out, go to hostel and sleep because you are not feeling well. Take rest. Okay. So two positive, there is a positive charges. 16 into 10 power minus 10, 12 into 10 power minus 10. Okay. So these two things are placed at a distance of 10 centimeter. So these are the two positive charges. Okay. So when these two things are positive charges, what kind of force will exist? Force of repulsion. Normally, by means of the force of repulsion, what should happen? The two charges have to move away from each other. Am I correct? The two charges have to move away from each other. Got it? But the two charges are not moving. The two charges are held together. So the same point in one or two situations yesterday I told. Whenever, in spite of force of repulsion acts, in spite of there is a possibility for the two charges to go away from each other, the two charges are not moving like that. In such cases, a kind of energy gets established in between them. So what is that energy? Potential energy. Remember, so the moment you see this type of situation, force of repulsion, immediately these two charges have to go. But the charges are not going like that. They are held at a particular distance of 10 centimeter. It's given. Yes or no? Means definitely there must be some potential energy in them. That's all. Understood? Okay. So look at this here. You see. So there must be some potential difference out here. There must be some potential difference out here. So initially, so the first charge, which is magnitude, what is that? First charge. First charge is what, man? 6 into 10 power 16 into 10 power minus 10 coulomb. Okay. So the second charge is how much? 12 into 10 power minus 10 coulomb. So the distance between them is 10 centimeter. Right? Yet 10 centimeters of distance, what happens? There will be some electrostatic potential energy. So electrostatic potential energy is equal to 1 by 4 pi epsilon naught Q1 Q2 by R. Okay, so this is initial potential energy. So initial potential energy is equal to 9 into 10 power 9 Q1 16 into 10 power minus 10 12 into 10 power minus 10 divided by R. So 10 power minus 1 meter. And if you simplify this 10 power minus, okay, so this is 10 power minus 9. This will get cancelled out. So initial potential energy is what? Okay, so 9 into 16 into 12 into 10 power minus 10. Okay, so Joule, potential energy is measured in terms of Joule. So there is initial potential energy. Now, in the second stage, what is he doing? The two charges are brought 4 centimeters closer. 4 centimeters closer means it is not the distance between the two charges, which is 4 centimeters. 4 centimeters, okay, so this is closer. Okay, one charge is moved. Now, in the second situation, so this is 16 into 10 power minus 10 coulomb. Okay, there will be some distance between these two charges, 12 into 10 power minus 10 coulomb. Now, what will be the new distance now? 6 centimeters. 4 centimeters he moved. Okay, 6 centimeters becomes the new distance between them. Then what happens now? Force of repulsion increases, with which potential energy increases. Okay, so now the potential energy, final potential energy is equal to 1 by 4 pi epsilon naught into 16 into 10 power minus 10 into 12 into 10 power minus 10 divided by. Okay, so this is 6 centimeter. 6 into 10 power minus 2 meter. 6 into 10 power minus 2 meter. Right? Okay, so 6 into 10 power minus 2. Now, so what I do is, see this here, so this into 0.6 I take, otherwise 6 into 10 power minus 1 into 10 power minus 1 only I will take. So this is 10 power minus 9. So these two things will get cancelled out. Therefore, you will be getting the previous format. In what way? So 9 into 10, 16 into 12 into 10 power minus 10 divided by 6 into 10 power minus 1. Joule. Now, what did we calculate here? Initial potential energy we calculated, and final kinetic energy, the potential energy we calculated. And if at all you calculate the change in the potential energies, the change in the potential energy gives you work energy theorem. Work energy theorem. In any situation, if kinetic energies arise, the change in the kinetic energies will be equal to work done. Or if there are potential energies in the system, the change in the potential energies will be equal to work done by work energy theorem. One of the basic theorems. Okay, so work done is equal to, so delta PE, change in the potential energy. So work done in this particular case, okay, so which is larger, which is smaller in this case? Final is larger. So potential energy final minus potential energy is, okay, initial. Okay, so this is 9 into 16 into 12 into 10 power minus 10. So this is common in both. Okay, so this here, this minus this. So I will be taking this as common. Okay, so work done is equal to 9 into 16 into 12 into 10 power minus 10 into. Okay, so in the denominator, what do we get? 1 by 6 into 10 power minus 1, which is 0.6 minus 1. Minus 1. Okay, so direct step I have written. Okay, so now you multiply 16 into 12. How much? 16 into 12. Okay, this is 72. Okay, 90 into 9.
70,
Into 9. Okay,
17, 28,
1728. 1728.
Total.
Total 1728. Okay, so 1728. 1728 into 10 power minus 10 into. So this becomes 1 minus 0.6 by 0.6. 0.4 by 0.6. Isn't it? 0.4 by 0.6. So 4 by 6, 2 by 3. 2 by 3. 2 by 3. So this 3, okay, we will cancel. So how many times? 5 times, 7 times, 6 times. Okay, so so 10 power minus 2, minus 10. Okay, but the standard representation is work done is equal to 1.152 into 10 power minus 7 joule. 1.152 into 10 power minus 7 joule. Understood? Like this. So there is a way how we have to work out the problem. 1.152 into 10 power minus 7 joule. Next, the people who have done, look at the fourth question, try calculate the electric potential at the surface of the silver nucleus having radius 3.4 into 10 power minus 14 meter. The atomic number of silver is 47. Yes, how much?
2.8 into 10 power 4.
2.8 into 10 power 2.8 into 10 power 4 plus 4 volts. Okay. That's here. Calculate the electric potential. Yes. Remaining answers, please. Sachin, what is it? Same thing here. 2 into 10 power 4. That means the minute page. Okay. Almost these two are close, but minute page. Right? Any more answers, please? Okay. Now, in this particular case, the given problem is calculate the electric potential in the surface of silver nucleus. So, if at all you consider nucleus as a sphere, okay, spherical shape, and for a spherical shape, what will be the potential? So, this is the center. Okay, now, so if at all some charge is given over here, right? Let the amount of charge which is present on the surface, that is a Q you say. Right? Q. Okay, now, in the case of this potential, remember, so what about the potential which is present on the surface? Potential remains the same even inside the surface also. But that will not happen in the case of intensity of electric field. That will not happen in the case of intensity of electric field. So potential, remember, in the case of potential, how much potential is present on the surface, same amount of potential will be there. That's why this we will be showing in the even the Gauss laws. In the Gauss law, so in one of the applications we will be getting, so integral 0 into dr, this is what we are going to get. So which is nothing but constants. Okay, so this is Gauss law application. Gauss law applications, so let's say in the Gauss law applications you will get. Understood? In the applications of Gauss law, you will come across that. Understood? Okay, so that's here. By use of this, what we have to conclude and what you have to remember is whatever the potential that you are going to calculate on the surface, the complete potential remains the same inside. Remains the same inside. Right. Okay, now then this is the distance that is R. Okay, so what is the potential for a sphere? For a sphere. So V is equal to 1 by 4 pi epsilon naught Q by R. So this is the potential for a sphere. That's a sphere. This is the potential for a sphere. Right? Okay. Now, nucleus Q we need to calculate. Okay, so charge on one proton. And how many protons are there? How many protons are there? Atomic number of protons are there. Atomic number means what? The number of electrons or number of protons. Or number of protons. Atomic number is symbolically represented as Z. Z into E gives you the net charge present inside the nucleus. Okay, so the atomic number is given, that is 47. So that is equal to 47 into 1.6 into 10 power minus 19 coulomb. So this is what the charge of the nucleus. Now, so what will be the potential over here? The radius, nucleus radius has also been given. So which is 3.4 into 10 power minus 14. So potential in this particular case 9 into 10 power 9. Okay, so charge that is 47 into 10, so 1.6 into 10 power minus 19 divided by R. R value is 3.4 into 10 power minus 40. Okay, minus 40. Right? Okay, so this any table can be cancelled in this. So second table only can be cancelled. This is 0.8 times. So this is 1.7 times. That's all. So this is the prime number. So 17. Okay, cannot be cancelled in any other. Like, okay, so then go for multiplication. Okay, go for multiplication. And coming to 10 powers. Even 10 powers also we will adjust. Okay, 10 power minus 14, 10 power minus 19, 10 power minus 5, 10 power minus 5, 10 power 9, 10 power plus 4. Okay, so this is 0.8, 1.7. Even the point also can be cancelled. 8 by 17. Okay, 9 8s are 72. 72 into 47. 72 into 47. Okay. 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 So 3384 divided by 17. 3384 divided by any points are there here? No points. Okay, 17. Right? So how many times? One time. Okay. Okay. So how much? Right? So here it is. How many times? 9 times. Okay.
150.
70?
150.
Oh.
79.
So exactly, it's going. Okay. 153. 153. So 8 times. 9.
168.
168, sir.
168, sir.
116.
150.
You got this. 90. Approximately 90 can be. 90 and the 4 is also there. No. Okay. Okay. 153. 10. Isn't it? No, this is 8 now.
199.
Okay. So this is 50. Okay. So how many times approximately 9 years of thinking? Approximately 9 thinking. So 199. Okay. So 199 into 10 power 4. So I want to put the point over here. So for that, what should I do? Okay, so B is equal to 1.99. 10 power 6 volt. So approximately 2 into 10 power 6. 2 into 10 power 6. Okay, like this. So this is the way how we have to work out the fourth problem. Okay, now coming to the fifth problem. 4 point charges plus 1 microcoulomb, plus 1 microcoulomb, minus 1 microcoulomb, and minus 1 microcoulomb are placed in the coordinates A, B, C, and D of A square of side length 0.1 meter. If E is the midpoint of BC, what is the work done in moving an electron from the center to E. Yes. First you draw the figure. When you give the diagrammatic representation, then okay, so it will be clear to you. Okay. In the meantime, I will give you the next problem also. Okay. Yes. So three more problems are there in front of you. Now we will discuss. Fifth one answer. Anybody, please? Zero. Huh? Okay. Who is telling zero? Sachin. So he says zero. Nucleus, keep the doors open, man. So outside, nice. The shower is coming. Inside, water droplets. See this, how nice breeze is coming. That we have to enjoy nature. And when outside is very pleasant, you are closing all the things. How can you enjoy, man? What do you? So that also you open. Just to clear, so open the door. So breeze, nice breeze is coming. Yes, good, very good. Okay. If water droplets enter, then you close. Okay, now fifth problem we have to discuss. Sagar, what do you say here? Fifth one? Huh? Zero only? Okay, yes, zero only. Okay, now let's look at this. Let me explain the fifth one. The given problem is 4 point charges plus 1 microcoulomb plus 1 microcoulomb minus 1 microcoulomb and minus 1 microcoulomb are placed in the coordinates B, B, C, and D of a square. Of side length 0.1 meter. So look at this, there is a square given here. So this is the square given like this. So these are the vertices A, B, C, D. Okay. So the midpoint of the square is nothing but point of intersection of the diagonals. Right. Now this is the midpoint of BC is given here. So this is B. Now from O to E in this direction you need to move an electron. An electron from O to E, you need to move. This is the diagrammatic representation of the given data in the case of fifth problem. In the case of fifth problem, right? Now, what is the work done in moving the electron across? The side length has been given. Okay, 0.1 meter, 0.1 meter. This thing 0.1 meter. Even this thing 0.1 meter. Even this is 0.1 meter. And how are the charges placed? So here plus 1 microcoulomb, here also plus 1 microcoulomb, here minus 1 microcoulomb, even here minus 1 microcoulomb. In an order I have taken. In an order I have taken. Okay. Now look at this. First of all, you need to calculate the potential. Okay. So due to all the charges, get the midpoints. That is the center. Right. Okay. Now potential due to A. How much? Potential due to A. Diagonally opposite I will take. Right? Okay. Potential due to A. So 1 by 4 pi epsilon naught, that is K. 1 microcoulomb, that is 1 into 10 power minus 6 divided by R. So what is the distance? R root 2 into 0.1. Can I correct? Yes or no? So this is positive. So potential get C is how much? Negative K into 1 into 10 power minus 6 divided by, so root 2 into 0.1. No, this is root 2, the total length. Now how? That's the 1 by root 2. This becomes 1 by root 2. This becomes 1 by root 2. 1 by root 2. 1 by root 2. Okay, now if you want to take the total of these two potentials, VA and VC, so this is positive and this is negative. So these two things will get cancelled out. The potential due to these two things will be 0 here. And at the same time, potentials due to this plus 1 microcoulomb and minus 1 microcoulomb, both the things will get cancelled out just like this. Therefore, get O, potential get O will be found to be 0. Okay, now coming to the second midpoint. So this is plus 1 microcoulomb. This is plus 1 microcoulomb. So equal distances. Equal distances. That means given the potential get E is also 0. Am I correct? Okay, so overall the potential difference between O to E is equal to 0. And what is the work done over here? So charge into the potential. Okay, work done. So 1.6 into 10 power minus 19, which is the charge of the electron, into 0. So 0 is the answer. Okay, 0 is the answer. Correct. Okay, so sixth one. A wire is bent in a circle of radius 10 centimeter. It is given a charge of 250 microcoulomb, which spreads on it uniformly. What is the electric potential at the center? Come on, please make it fast. So fifth one is over. So I am erasing. Okay. Sixth one, a wire is bent in a circle of radius 10 centimeter. It is given a charge of 250 microcoulomb. Yes. How much? 2.25? 2.25 into 10 power minus plus ah, 7 volt. Okay, so let me work it out. Same answer? You do it? Okay, so a wire is bent in the form of a circle of radius 10 centimeter. So look at this. That's here you see this is the circle of helix, and this is the center. And what about 250 microcoulomb of charge that is placed on the wire throughout the circular region? The charge is distributed uniformly. What is the electric potential at the center? Okay, so there is a uniform distribution all over the length of the circle. All over the length of the circle. So look at this, all over the length of the circle, uniform distribution. Uniform distribution. Okay, to measure the electrostatic potential, first of all, you need to calculate the total charge. Yes or no? Okay, now the total charge, there is a Q you say, but how much charge? So look at this, for the purpose of a small elemental. Okay, length I will take in the elemental charge I will take over here. Elemental length over here. right? Elemental length. Okay, so now, so there's the charge present on that dq. So dq will be how much? So that will be lambda into dl. Am I correct? Lambda into dl. Lambda into dl. Right? Otherwise, only dq you take. And if at all you get confused with this lambda into dl and in the integration total dl which is 2 pi r. Okay, so if at all you feel that 2-3 steps extra will come, so that dq will take, no problem. Okay, so this is at a particular distance r. Now, so with respect to this dq amount of charge, what will be the potential at this point? Now you have to look at this as a point. You have to look at this dq as a point charge. Such point charges, how many are there on the entire ring? Infinite. Okay, so this again, the electrostatic potential due to that is dV, small elemental potential. So 1 by 4 pi epsilon naught into r. So this is dq by r. Now for total potential, you need to integrate this dV between the limits 0 to q. Okay, so V is equal to integral 1 by 4 pi epsilon naught, so dq by r from 0 to q. So V is equal to, so 1 by 4 pi epsilon naught r integral dq from 0 to q. So this is V is equal to 1 by 4 pi epsilon naught q by r. So this is okay, the potential equation in this particular case. And the radius has been given, that is a 10 centimeter. Radius is a 10 centimeter, which is nothing but 10 power minus 1 meter. And what about the charge that is given? So this is 250 microcoulomb. So this is 250 into 10 power minus 6 coulomb. So this is 25 into 10 power minus 5 units. Then the potential is equal to 9 into 10 power 9 into, so 25 into 10 power minus 5 divided by r 10 power minus 1. So this is 10 power minus 4, this is 10 power 5. Okay, so V is equal to how much? Okay, isn't it? Into 10 power 5. 225 into 10 power 5. So this is 2.25 into 10 power 7 volt. So this is what the answer. So the answer is correct. That answer is correct. Come on, note it down. Hello? So what is the answer of the seventh one?
5 into 10 power 3.
5 into
10 power 3.
5 into 10 power 3.
3 into 10.
3 into 10 power 3 or 5 into 10 power 3? Both are answers. 3 into 10 power 3. So there are two answers. Okay. So let me discuss. Huh? The seventh problem is that 2 point charges are placed on the x-axis. A 2 microcoulomb charge at x is equal to 10 centimeter and minus 1 microcoulomb charge at x is equal to 40 centimeter. Calculate the electrostatic potential when x is equal to 100 centimeter. And all the three distances are taken along the x-axis only. All the three distances are taken along the x-axis only. Okay. So the distances carefully we need to handle with it. So in this seventh problem, hello? Yes. Okay. Okay, so there's a 2-point charges are placed on the x-axis. A 2 microcoulomb charge at x is equal to 10 centimeter and a minus 1 microcoulomb charge at x is equal to 40 centimeter. See here, the given situation I will be taking over here like this. So this is the x-axis, right? So this is the origin. I will be taking the scale like this. This is 10, 20, 30, 40, 50, 60, 70, 80, 90, this is 100. Okay. So plus 1 microcoulomb of charge. 2 microcoulomb of charge at 10 centimeter. So here this is 2 microcoulomb. Next, at 40 centimeter of distance, minus 1 microcoulomb. So this is minus 1 microcoulomb. Okay. Now you need to calculate the electrostatic potential at 100 centimeter. See here, this is the point P given. So here, potential, okay, at this point. So this is equal to how much? Potential at this point is equal to how much? Okay, so this is A you take, this is B you take. So potential due to A is equal to at that point. So what will be that? 1 by 4 pi epsilon naught, okay, into, so charge Q, that is 2 microcoulomb divided by the distance between A to P. Okay, so potential due to A is equal to 9 into 10 power 9. This is 2 into 10 power minus 6 divided by, so what is the distance between A and P? Okay, 100 minus 10, that is 90. 90, right? Okay, so this 10 power 8. 10 power 8. Okay, so this is became okay. 10 power minus 2. In terms of centimeters, it is given. Okay. 10 power minus 2. 90 into 10 power minus 2. Right? Okay. So this 10 power minus 2 in this 10 power minus 4. So this becomes a 2 into 10 power 4 plus 4 volts. Yes. Okay. Now potential due to B. This is positive. Positive potential. Okay. So potential due to B, how much? 1 by 4 pi epsilon naught. 9 into 10 power 9 into Q. Q is minus 1 into 10 power minus 6. The distance between B and P, 100 minus 40, that is 60. Okay, 60 into 10 power minus 2. 60 into 10 power minus 2. Okay, so this can be written as 6 into 10 power minus 1. 6 into 10 power minus 1. 10 power minus 1. Right? Okay, so this 6 here, 3 times, this is 2 times. So VB in this particular case, negative 1.5 into, this is 10 power minus 5, 10 power 4, 10 power 4. Okay, volts. And what is the total potential now? The total potential get P in this particular case. So potential get A plus potential get B. So because it is a scalar quantity, potential get A is plus 2 into 10 power 4. This is minus 1.5 into 10 power 4. The answer is 0.5 into 10 power 4. 0.5 into 10 power 4. Or 5 into 10 power 3. Or 5 into 10 power 3. Okay? Correct. Your answer is correct. Okay, next problem, there is date 1. 2 point charges plus 40 microcoulomb each are placed 20 centimeter apart. What is the potential at the midpoint? Okay. How much? Answer? 7.7. 7.2. 10 power 6 volt. And okay. So there is an answer they say. Right? Girls, Suhasini, same answer? Okay. So this let me check it out. Let me check it out. See, the problem is 2-point charges plus 40 microcoulomb each are placed at 20 centimeter apart. What is the potential at the midpoint? What is the potential at the midpoint? Look at this. Here you see. Here 40 microcoulomb, even here 40 microcoulomb. The distance between these two things is 20 centimeter. At the midpoint means that this is 10 centimeter. This is 10 centimeter. 10 centimeter and 10 centimeter. Now that's the midpoint with C you say. Okay, so this is A and this is B. So potential due to A is equal to how much? So 1 by 4 pi epsilon naught, which is equal to 9 into 10 power 9 into charge. So that is a 4 into 10 power minus 5. So divided by, so R. So that is 10 power minus 1. 10 power minus 1. 10 power minus 1. Okay, so on simplification, so this becomes a 10 power minus 4. So VA in this particular case 36. Okay, into 10 power 5. Right? Next, so potential, this is positive. So potential will be also will be having the same value. 10 power 5. Okay, 36. Right? So total potential is for VA plus VB. So the total potential is equal to 72 into 10 power 5 or 7.2 into 10 power 6. Yes, you are right. Two charges plus 10 microcoulomb and minus 5 microcoulomb are 10 centimeter apart. Calculate the potential at point P at a distance of 1 meter from either charge. Either charge. How much? 4.91 in 10 power 4 volt. Okay. Some answer has been told. Okay. The remaining people just keep trying. In the meantime, I will be going for this next problem also. That is problem number 9. Okay.